So hello, hello. So let's continue our discussion of models and for the dynamics of infectious diseases. And today we want to get more to the models, not only to the qualitative discussion that we had yesterday. But we want also that our models somehow reflect some of the things that we have discussed yesterday. So, the general approach to the more classical way of modeling infectious diseases, which is to divide the population, and we are talking about humans, the population, into classes, right? And then you will have classes, and that means that every individual can be in one class. So, for instance, you can be susceptible, you can be infected, you can be asymptomatic, you can be recovered, and so on, so on. So many possible classes of a person can be in a class, and then we would talk about the total number of people in each class, and we want to study the dynamics as the people go from class to class. We'll generate a population dynamic, and we want to discuss this. Okay? So usually this is made with drawing something like this. Say S is for susceptibles, and then you have an arrow that indicates where it can go, and then let's say it can go to infectious, okay? And then, well, that can go maybe to recovered. So this is the SIR model. It's the simplest, okay? Not the simplest. Could also get other models here. Okay, also simple. We actually will start with this one. This is SI. Like this one. Okay. So let's think a little bit. What kind of situation would be modeled by a model that has only S and I without arrow back? HIV, yeah, HIV is usually more complicated. You need intermediate classes. Diabetes. Diabetes is not infectious disease. Yeah.
Maybe something like food poisoning.
Which is also not infectious disease.
Mm-hmm.
But okay, there was a hand I saw. Yeah, leishmaniasis. Yeah, leishmaniasis is different because leishmaniasis is transmitted by mosquitoes. It's not mosquito. It's something else. But yeah, but infectious people do not. Yeah, okay, leishmaniasis is not bad because, yeah, okay. So, one thing. Usually there's also a notation here, which is you put a dotted or line like this, okay? Pointing here, saying that from S to I, you have to be in contact with I, which is not the case of leishmaniasis, okay? But, okay, if without this, leishmaniasis could be one. Yeah.
It could be, for example, some sexual diseases as gonorrhea, or maybe diseases like influenza where the virus has a high mutation rate, so you can consider that the immunity is not that important.
Yeah, but then you don't have immunity, you go back to S.
Uh-huh.
Right here you are not going back to S.
Oh, okay.
Yeah, maybe Chagas disease.
Chagas. It's much more complex that, okay. But I mean, you think that people will stay infected all the time, but there's another possibility.
You can think of those viruses which interject their DNA to the cells, so essentially people won't be susceptible never again because they'll always have the something like HIV or others with reverse transcription.
Yeah, okay. HIV, in order to write something meaningful for HIV, usually it is you need to introduce latency, because this is latency and asymptomatic phase.
I have an idea, but it is not an infectious disease. But I have an idea. It is not an infectious disease, but it is modeled with these kind of models. Gossip spread.
Gossip. Yeah.
You have the gossip. You already know it, and that's it.
So, okay, without this error here, I mean mid-error. Okay, mid-error. Sorry, with this one here. Well, this is used for something else actually, because it's not that the people remain infectious forever; they can die. Okay, and then obviously, okay, then they would die here, and this is used for deadly. Deadly infectious.
So there is rabies disease, HIV, and also Ebola. It's a
But
viral disease.
not Ebola. It's you get recovered at a certain point. Not everybody dies. Yeah. Yeah, it's not everybody dies, but okay, high mortality. Yeah.
I think that I don't know how to say that in English, but hepatitis.
I would say that right
hepatitis.
now too.
It's a persistent infection.
But
Then
you don't. It's not infectious usually. Yes.
Not. Yeah. Hepatitis is infectious.
Hepatitis
Yeah.
C. Yes. Ah. Okay. Yeah.
You will stay with a persistent infection.
Yeah. That's true. Yeah. Okay. Hepatitis C. Yes. So, okay, now let's move to the next thing. Let's say that you get back to the susceptible class. Okay, what kind of thing would be this? Flu. It's a little bit different because you have a transitory. Transitory immunity, okay. Yeah, so this is usually more like
It could be like
bacterial infections or rotavirus, for instance.
Yeah,
You don't have immunity to rotavirus.
yeah, I would say the enterovirus that.
This kind of thing is.
And what about herpes?
I don't know much about herpes. So.
Yeah,
but I mean, do you get back to susceptibles?
No.
No, then okay,
you are
then it's
always
not.
infected.
Here you have the dynamics where you get back, okay? So you don't have any immunity in this case. So this is very particular because most of the time, what you would expect is something like you go to eye and then you recover and you are immune, but eventually immunity can be not long lasting and then you would go back here. Okay, this is more applies for many diseases. Okay, but this one it's more like the ones that we talk. Okay, it's bacterial or enterovirus, rotavirus, things and so on, which have no immunity at all. But the more common situation is going to S to I and to R, which if immunity is waning, it's decaying with time, then you get back here, and then you have what people call an SIR model. This one is SIS model. The other one was SI, and this is SIR. Okay, so I'm playing around with S, I, and R. Okay, now let's have a precise interpretation of what this means. Okay, so S is the number of susceptibles. I is the number of people that are infected at a certain point of time. And this is the number of recovered. Okay? So now think you have data. Like with COVID or something, you have data. What is the kind of data that you will get? Okay? So you see this epidemic curves that people draw, yes? This kind of thing. We have seen this with COVID, okay? So, but does it correspond to which variable here? Usually, what you hear when you say in the news, let's think of COVID. What do people say usually? The new infected. Okay, new infected per day, which is not I. Okay, that's a very common error that we see when people more distant from everyday life, it's just more mathematicians and so on. They fit the I will fit data and so on, and they fit I to the data of new cases per day. It's completely wrong. Okay, so you never do this. Now, can you know the number of infected people?
I think that exactly we can't know, but if you estimate the time of infection, you can make like the calculus of the new cases, the time that it will remain infected, and the new case of the day before, and make something like this.
Yeah, you could do this. Yeah, in theory, yes, but in practice it will not be like that because. Why? Usually, you have here an observational problem, okay? So it depends on which disease you're talking. You have a problem of surveillance, okay? So, assuming perfect surveillance, then you would say the number of new cases reported today is 200. It's not one. I got all the new cases. Okay? All new cases. This kind of thing. So all new cases today. And assuming that once you get the infection, you're infectious at the same time. Okay? Which actually is not true for almost any case. Okay? Then it would be theoretically possible to have I. But there are many problems with I. One of the main problems is that surveillance is usually not perfect unless this is an infection that has an aspect. It's severe, so that everybody that gets the infection has to go to a hospital, and then the hospital can make a notification. Okay, but otherwise, for instance, flu. Modeling flu is hell. When you don't have the numbers, people don't go to stay at home. So there's a lot of people that are not notified, not because the surveillance is bad, but people don't go for the health system. Okay, so I is difficult to get, and even the total number of new cases is usually very difficult to get. Okay. So now you could say, what are things that are easier to get? Okay. So, for instance, with COVID, also with other diseases, that there's for instance, flu. There's a certain number of people that require hospitalization. Yeah? So hospitalization is much easier to have the notification, okay? So a better data, I mean, a better fitting a model would be easier if I have, if I can fit the number of people that have been hospitalized, okay? So what I need in this case is to introduce a new class here, okay? So I do something like that. So I can, from infected, I can maybe go to either to R, recovered immediately, or I get to hospitalized, and then I may be recovered, or maybe I die. So it's increasing the number of classes, yes? And then you see that if you want to be more realistic, the number of classes will be large, yes? So there are many situations where just playing with S, I, and R is not sufficient, okay? So, for instance, a disease that you can only measure the number of hospitalized people, you need the hospitalized. Maybe you can also get the number of people that died from this. So these two can be used to fit your model to data. Okay? It's better than the others. Okay? So the model and the compartments in the model, that when you try to do something more realistic, you have to have the compartments which you can connect to the data. And then you have to know what kind of data you have. It depends on the disease. And what kind of notification system, of surveillance system is providing this data. Okay? So this is important as a modeling philosophy, a modeling frame of mind. Okay, so that you do things that are realistic, and if you want to work with data, then you need to have the right compartments. Okay, and you can take many things more here into consideration. For instance, you could model here the people that have to be hospitalized, but maybe there are people that have to be hospitalized, but there is no hospital. They can't get a place at the hospital. So then you would have a new class here, which is the people that are not hospitalized, okay? But should be, and then they have probably a higher death rate here, and a smaller recovery rate here. Okay. So this is also important, and this can be dependent on the size of your hospital beds, okay? How many people you can have. Yeah.
How would you define the hospitalized? Like, what would be like the symptoms that people would show that would show us that she or it needs to be hospitalized? Yeah. So this depends on the disease. So there's a certain, every disease has a certain etiology, but sometimes, defining who is hospitalized is it's the person that is in the hospital. Okay, but more difficult is who are the people that should be at the hospital and are not. Okay, so this depends on the disease. If you think COVID, that is usually the people that have to be hospitalized is the people that have severe respiratory problems. Okay? And if you don't get to the hospital, you may end up dying. For instance, this is one case which was famous because of everything that happened in Manaus and so on. But for other diseases also, you may have to go to a hospital, and maybe it's a place with very poor, like the situations where you sometimes have Ebola, Marburg, and this kind of things in Africa. There's not enough place in the hospitals, but sometimes it's clear that the person needs it. Okay? So it's not super well defined usually, but
it's important also, because so then you could also have more things, because here this one could be subdivided in normal, hospitalized, or intensive care units, okay? Which you then point from here, then it can go from here to here if you get, or you can go from here to here, and so on, okay? So lots of things, right? And why would this be important? If you want to model things, you have to know how many ICUs and how many normal beds you need. Okay, so maybe you have a certain limited capacity here. Okay, so using this kind of thing, this can be taken into account. Okay, so then also in more realistic settings, you would also like to take into account certain heterogeneities in infections in the process of getting infected, and the most common one is depending on the disease. The most common one is taking into account the age of people. So you divide the population in age classes, and you will have different. You maybe have all the same kind of diagram, but with different parameters. Okay? But if you divide your population into classes, these classes are obviously in contact. Say you have just juveniles and adults. Okay, 2 classes only. Okay, and then you will need to know the rate of contact between juveniles, because juveniles have contact with juveniles, adults with adults, but there's also between both. And if you have the more classes, say you have 3 classes, you have to know all the contacts between the classes. The frequency of contacts. And this will generate a matrix, which is called contact matrix. It's a matrix where you have, say, class 1, 2, 3, 4, class 1, 2, 3, 4, let's say up to teenagers, then you have from 20 to 40, from 40 to 60, and over 60, something like that. And then you have here a frequency, we'll have numbers here, and which will be the frequency of contacts, and you have to put this into your model later. Okay? This represents a problem, because how do you know this frequency of contacts? Okay? Yeah, first question.
Professor, we have like all these many things we can do to try to improve our model, but what's the point to stop? Like they keep improving the model, or we come to a point we have like too many parameters to estimate?
So you have to have in your model things that correspond to 2 things. First, you have to have a point where to fitting your model. Okay, finding the best fit. Okay, and this you do usually with more complicated things like log likelihood and so on. And then also you have to know what kind of answer you want from your model. For what is the model being built? Okay? Is it to give advice directly to a certain situation, a certain place? Then you need a specific model with a lot of specificity. Now, what we will do in a moment is to write something very simple. Very simple, you just think that very simple things give you insights of the general behavior of what you expect from epidemics. But the very simple models are usually not used when you have, say, You go for São Paulo and you work with the Secretary of Health, and they want specific answers to specific problems. Okay, so for instance, I had been in touch in 2020 with people from the municipality of São Paulo, and the people that were in charge of how many graves you need for people that die. Okay, so they want an estimate of this. For instance, that's important for them because, okay, what should we do? Should we just continue as we are, or can this increase? So then they want this kind of thing. This is what is I think that is usually useful, because models can be two things. One is to just give you a general view of what you expect and understand. So that in this case, you are more close to basic science, actually. But if you want the models to work in the real world, they have to be more complicated. Yeah. Okay. Yeah, more?
And just to have some idea, for example, to estimate the number of infected people, if we compare a SIR model, a basic model, to one of these that has many classes and estimations, how the models compare?
No, the number of infected people is not. It's usually not available. You never get the number of infected people from the data. Never. Okay, because surveillance is always a problem. Most diseases have either latent or asymptomatic cases. So only in very particular cases like Ebola and so on, you get the number of people infected. But what you get easier is things like, as I said, hospitalizations, or for instance, how would you model influenzas? That's a crazy thing. Okay, so if you have only, you have a problem, which is how. So people don't go to the doctor, so you never get the number of infected people. Okay? But sometimes they go, right? But they go to random people, okay? People that not necessarily in a hospital. Okay? So this kind of notification is really very bad. Okay? So what surveillance should do is to have sentinel hospitals, which report every case, not only of influenza. Every person that goes there will have a report saying person has been diagnosed with this and this. And these sentinels then will give you an idea, like a proxy of the dynamics. Okay? And then you try to use some statistical models to infer the size of your number of infected and number of people at risk, so on. Because there are things that are also important that you have to take into account sometimes, and many times, is, so this is a population. So is everybody in the population here? Okay? So not necessarily. There are people that maybe are not at risk, okay, of certain diseases. If there is a disease that has a strong behavioral or societal component, maybe the people at risk, okay, are not the total population. So, for instance, I remember that it was a crazy thing. A paper that, it was not published at the end, but it was around in the time of Zika epidemic, and there was a Zika calculation of Zika epidemic, I think in Colombia. And you had the Zika at a certain point. It was really concentrated in some cities, okay? But the model used the total population of Colombia, which is bullshit. Okay? It is because it was spatially contained. Right? So they try to calculate the R0. But you see, you have to take into account which is the population that really is important for you. Okay? So if you have a sexually transmitted disease, it's a population that's sex-relative, active. Okay? Okay, so having said this, let's go for the simple things and write some equations for simple models. But keep in mind, these models will just give us a general view of how epidemic modeling is used, but they will not be the models that if you go to work with this, you will have to be more specific than the models that I will discuss now. Okay? So let us begin with a simple one, which would be the model of S going to I and going back to S. Okay? So you have two classes, and we want to write the how these classes change in time. Therefore, I want to write ds dt, and I want also the I dt. So I will consider the population as closed. Okay? And well, in order to S to change, and it can change, what do you expect? You expect first that there is some S, somebody in the class, okay? So usually you would write this, something minus, because infection should take you out of the, if you get infected, you get out of the class, and you get into this class, okay? And then you get out of this class and go here. But before we do this, so just for the names of things, this is called the force of infection, lambda. Okay, but the force of infection has to be something which depends on the number of infected people. Okay? So what would you write here? The usual thing is put minus something which is I, and then some constant here, okay? Beta. And this is like predator prey. So the S is the prey, I is the predator. So this, but with efficiency 1, okay? Now, let's think about this here. Yesterday, we discussed the case. We discussed that epidemics from a given disease are more or less the same, independent of the size of the city or the state. Okay, so you would, in order to have this, your dynamics has to depend only on the fraction of susceptibles and the fraction of infected or the other classes, only the fractions, okay? So this is not the case here, because if I divide this by n, say the population will be constant, okay? So there's a total population size, which will be n, which is S plus I, and I will write a model that conserves this, okay? So if I want this, then I could divide this by n here, and by n here, and here, same thing. But this depends on I, not I over n. Okay? So I have to modify this equation and say this should have an n here. So if I divide by n here, I have S over n, and I divide S on this point, I will have S over n and I over n. Okay? So and now this already looks a little bit like what we had discussed about R0 and so on. So this is the number of susceptibles is decreasing. This term is the number of new infection. It goes here. And the number of susceptibles is decreasing, and it's proportional to the number of susceptibles times the fraction of infected. Okay. So this reminds us from yesterday calculation for R0, yes? And this is the typically the infectivity parameter beta, which is not the same beta as yesterday, because yesterday I considered beta just just the probability of infection. Okay. Now here this is more or less this, but here this also has the famous number of connections and so on and so on. Okay? So, but well, this model has the possibility of going from I to S, but I to S does not come from the fact that I is in contact with S. It's just natural that doesn't have immunity. So after some time, it will be like a term, like a death term. Okay, and then this goes here, and this is the model. And so, okay. Hypothesis behind all of this is that I'm taking a population that is well mixed. So well mixed means that potentially everybody can have contact with everybody, and everybody has the same number of contacts per unit time. Okay, so as we discussed yesterday, certain disease this will not work. Okay, but well, for many diseases this works. Okay, so that's one of the hypotheses. So now that's the model. Okay, and the model is this is the simplest model, and this is the model that I think is the only one that we can solve. Okay, let's see how we can solve. Because you see, if I add S and I, then this cancels with this and this with this, therefore the total number of individuals in the population is conserved and it's consistent with my hypothesis here. Yeah.
Question. I didn't understand the part where you divided by n, the derivative. You said that you couldn't do that, like ds divided by n. I understood like the infection divided by n, that is a fraction of the infection.
Yeah.
But I got a little bit lost when you divided the derivative by n. You said you wouldn't do that.
Yes, I mean, n is a constant. Okay.
Okay.
So
Yes.
I can just go. Let me do here. I can just write this and divide by n, which is the same thing that this. Okay, because it's a constant. So that's the fraction of susceptibles. And on the other side, you have minus beta times E times S. You already had one n, and then you have a second n. Okay, n times n minus me. So dividing both sides. Okay, so this is S over n. This is I over n. This is S over n. This is I over n. These are the fractions of infected and susceptibles, and the equation depends only on the fraction. Okay. So therefore, the total size of the population is not coming into the play. Okay? It's frequency dependent, not population size dependent. Okay? And we want this because we discussed this is realistic, that the population size in humans of a city, for instance, is not driving it's unless it's very small, but usually you have the same characteristics in cities of different sizes, or states, or countries. So now I can write, let me say the best way. Okay, I can write here S is equal to n minus I. Okay. And then I can substitute in the second equation. Right? Okay, that's an equation only for I. Yeah. So if I rearrange things here, minus me. Yeah. I will have this beta okay, beta over n times I have the linear term I, which is beta no, I made a mistake here. No, I didn't make a mistake. Okay, yeah, I made a mistake here. There was no n here. Okay, because this is I, and this is s over n. Okay. So I is multiplied by one term is beta and the other minus gamma, plus minus a term which is beta I squared over n. Is it correct? Yes. Ah, good. So now I can rearrange this in this following way. That is beta minus mu times I minus beta. Beta minus I divided by beta minus mu times I squared over n. Yes? And finally I get this here, which is beta minus mu times I times 1 minus beta I squared divided by n times mu minus beta minus mu. A logistic. We know how to solve. We are feeling at home, yes? Logistic equation. Okay? And carrying capacity is it's not the squared. Okay, sure. Yeah. So the carrying capacity.
Professor.
Yeah.
I'm having trouble understanding the n. We divided, like we changed beta. We did some normalization.
By the calculation or here?
Here, there.
I'm just saying that the complete equation has to have this n. Okay?
Okay. And the derivative is the derivative of s or s over n?
Oh, it's s. That's the equation.
Okay.
Yet the point is that this equation implies frequency dependence. Frequency dependence means that if I divide both sides by n, I get an equation for the frequency of susceptibles in the total population, s over n. Okay? And that is I over n. It's also the frequency. And then I will have s over n and I over n. It's also only frequencies. Okay? So that's frequency dependent, which means that you have a dynamics for the proportion of people that are susceptibles and infected, not depending on how large is your population.
Okay. It's because we had the same equation without the n before, and now it has n.
Oh, okay. I mean, I did the one before that was a different beta.
Okay.
It's just a name for the constant. Okay.
Okay. Thanks. Now I understand.
So. Okay. You need an equation which is only frequency dependent, in order to incorporate a known fact that the dynamics of most of the epidemics is not dependent on the size of the population, like São Paulo compared to Santos or to some other places. The dynamics we see with COVID, it's more or less the same. I mean, it's about the fractions, not about the total population. So. Okay. For instance, you don't want your R0 to depend on the total population. You want it to depend on fractions only. Okay. So, okay. Now this has a certain carrying capacity, which is n times beta mu divided by beta. Therefore, this is n 1 minus mu over beta. That's the carrying capacity. And the dynamics is just like this in time. This is I. Then it will start and then it will go to a fixed point, and the fixed point is given by this. Okay? That's the carrying capacity. So, now, we have here beta minus mu here. And here we had also this. So in order to make sense of all of this, beta has to be bigger than mu. Okay? So you need beta minus mu. I mean, in order to make sense. In order to have given a small initial population, okay, which when you can just neglect this term here, then they have an exponential growth at the beginning, which is here, like every logistic case, with a parameter of growth which is beta minus mu. Okay, so beta minus mu has to be bigger than 1, bigger than 0. Sorry, in order to have the invasion. Okay, this is the criteria for having an epidemic. Okay, so I can rewrite this as beta over mu, like this, and I will call this R0. Okay, because this is the why I call him this R0. This is the condition for having an epidemic, for the possibility of your pathogen, your infectious agent, to invade the population of that is susceptible. Okay, so when you start with a small number of infected individuals, then your population is essentially susceptible, and this is the condition of invisibility in ecological terms and in terms of epidemiology. This is usually the epidemic threshold, if you want. Yeah? And here you have K is equal to N, okay? 1 minus 1 over R0. Okay? So this is the equilibrium point. It goes to an equilibrium. Right? So, and the equilibrium is determined, the fraction of I mean, the number of people in and the equilibrium state is determined only by R0. Okay. Now, pay attention to one thing, which will be true in other models also, that people usually want to know R0 because R0 determines the initial growth. It's the invisibility criterion, but it also gives you the size of the equilibrium. Okay? And in the next models, it will be more or less also this. So it is not. It can be measured in principle, could be measurable at the starting of the epidemic, and then you would know where you go. Okay, so you say you are in a situation that you start and you have only this let's say, and you fit an exponential. When you fit an exponential, you will have an exponential of beta minus mu times t. Okay? Which is equal to e to mu r0 minus 1 times t. Okay? Yes? So, problem. So, we have seen a lot of people with COVID stories and so on talking about R0, and usually what you want is R0, that you could measure this at the beginning of an epidemic, because it will also tell you how severe will it be at the, not severe, but how large is the equilibrium point? Okay, if I get the R0 here equal to say 2, then the carrying capacity will be just 0.2 or 0.5. But if R, for instance, is like 10, then it's 0.9. So you have an important information. But you have a problem, which is you can only measure this thing here. It's not this is the thing that you can fit here, but it's not R0. It's mu times R0 minus 1. Okay? So maybe you know mu. Mu is the typical time of infectiousness. Okay? Here. Okay? That's 1 over mu is a time, and this is typically the time a person stays in the infected compartment. So this is more or less the duration of the infection. Maybe you know the duration of infection, then you can, from this, get to this. Okay? In this case, which is very simple, in more complicated cases, it will not be like that. And actually, there is a way of calculating R0 without model. This is a more advanced topic. I don't think I have anything to say about this in this course. So, very good. We have so this is a model that is solvable. Right? This is the simplest model you can have. Now let's move for SIR model. Okay? Which is most of the time that's the simplest model that can be applied to at least to have general ideas for a certain number of diseases. As I told you in the very beginning, SIS model is only if you don't have any immunity. So it's rather restricted application. Okay, but I'm discussing it here because it's very easy to introduce R0 definition and also to calculate the people at the equilibrium. Let me before we go to SIR, another thing. So you get to an equilibrium, okay, but this doesn't mean there is no new infections. Okay, so get to equilibrium here. Okay. That means that you will have dsdt and didt equal to 0 at the equilibrium point, okay? Which means that this is the number of new infections, okay? And this is the number of people coming in, so they have to balance, okay? So the number of new infections is not 0. So there's just an equilibrium. Doesn't mean that you got to this point. And the people say you have the carrying capacity here, okay, and then there would be a fraction of people that would not. I mean, if this is 0.5, then there's the other 0.5 people that you could imagine maybe they are remaining susceptible, but it's not true in this model. It will be true in the other model, but in this model it's not true because you get to an equilibrium, but just it's an equilibrium where you have infections equilibrating with new susceptibles coming from the infectious people that have no immunity. Okay, so doesn't mean that people in this case we can have no information about how many people got actually infected, okay? Because they are not doing it at individual level. But here will be better for this. So now, and I don't want, I want these people which are removed to be immune forever. Okay? So great. Yes? I don't have an error from here to here. So this first part, and I here infection comes through contact between both of them. So I will have ds dt. Well, I have to write this. I have to write this. And I have to write this. So ds dt, by the same reasoning from the SIS model, is beta times S times E over N. Okay? With a minus sign. Yes? The same reasoning. But now there's no other term here because nobody is getting susceptible again. And we are considering a population that's closed without dynamics of birth and death. Okay? It means when it's dotted means that you get to I coming from S through contact with I. Usually you can omit this, but sometimes people draw it this way. And sometimes also in some publication you see something like this. Instead of this, they put the rate here. Okay, they would put the rate of S, that would be minus beta I over N. They write it here, so I think that's. But we write it on an equation. Now, the number of infected is the people that got actually infected, coming from the susceptibles, but they stay infected for a certain period. And then they are not anymore infected. So it's kind of mortality of infected and mortality in not that they die, but they are not anymore infected. Okay? After certain typical duration of the infection. And then this will go to the immune people, they removed, and this is the model. Okay? So, now, this model we cannot solve in analytical terms. We cannot do the same thing that I have done with SIS. But maybe we can have a lot of information which is important, and sometimes you really want more qualitative informations when you don't have very good surveillance anyhow. So the first thing is epidemic threshold. So I would say I have an epidemic if when S is very close to N, okay, at the initial point. So S is actually N, and you have only one tiny fraction of infected people at time 0. I will say I have an epidemic if di dt at time equal to 0 is positive. Okay? Therefore, the number of infected people will increase. Okay? Well, then later there will be whole things happening in the dynamics, but at the initial point, I want di dt equal to positive means that it's an invisibility criterion. If you have a small introduction of a small number of infected, it will increase. So, but this is very easy to, if you look here from this equation, and you put S equal to N, then di dt is equal to beta times I minus mu times I. Okay, so therefore, I need beta minus mu positive, therefore beta over mu is bigger than 1, and this is R0 is beta over mu. Okay? It's the same expression we had here, actually, but only that this mu now is the duration of infection, but you go to the recovered and not back to the to the susceptibles. So this is R0, and this is the condition that you have an epidemic. Now you may want to have a look at the solutions. Okay, so there's something that you can immediately see is that the derivative of S is always negative, can only decrease, and this one can only increase. And this one can have increase and decrease. So you will have something like this in time. You have S will decrease.
Professor,
Yeah.
sorry. In this model, we are considering that the immunity is only acquired by the infection.
Yes,
right?
yes.
If we want to include natural immunity, do we need to add?
So natural immunity, you mean people that have natural immunity.
Yes.
Okay, then your population at risk doesn't have these people. You just consider that N is not the total population, it's the total population minus the number of people that have immunity. Okay. Well, you could have things like vaccination and so on, that it's different. Okay. But a natural immunity is just that the population at risk is smaller than the total population. Okay. So S goes like this, and I will be something that usually increases exponentially. Why? Because at the very beginning, okay, here it's time 0, okay, it is linear. Here it's an exponential growth. Okay, so it starts exponential, then it gets some inflection, then it will go here and go here. It is not symmetrical. It's not symmetrical. And R. So how do I know this? Through numerical integration of the equations. Okay. So it will be something like this. Starting from 0. Suppose that well, there's no other way of including natural immunity. It's saying that at the time 0, there's R, the recovered is not 0. But usually we start with recovered equal to 0 because we don't have anybody that had been infected at the beginning. But one way it would be to say, okay, then R is already something. Yeah. So, and this value here will be R at infinity. And what is R at infinity? Is at the end of the epidemic, the number of people that get recovered is the number of people, total number of people that got infected. Okay? So here, this goes to 0. This doesn't go to 0 necessarily. Okay? And this reaches some R infinity value. Okay? Now, very nice. It's easy to calculate this peak here. Okay, R I peak. Okay, that is very easy because at the peak. Let me see. Okay, and it's not very easy to calculate it this way, no. But at the peak, di dt is equal to 0. Okay? That's when the derivative is 0, and this oops. This means that this has to be equal to 0, so beta times S at the peak divided by N, and I can factor out I minus mu is equal to 0. Therefore, S over N, the peak happens when S over N is equal to mu over beta, which is 1 over R0. Okay, that's what the moment the susceptible population gets to this, then you have the peak. Okay. Okay. Now, it's not so easy to calculate the value of I, but I can calculate something else. Okay.
Professor, in practice, sometimes we use this to estimate when we are at the peak of infection.
In practice, no. I mean, practice is different because, okay, this is obviously the condition to know when you're at peak. When you don't know S, usually. Okay, you don't know S. Okay, again, usually in this mathematical formulation, yes, that's the characterization of the peak. I know R0, which I could know from the very beginning. Then knowing R0, I know where the peak will be. But in practice, for instance, with COVID, there have been lots of discussions, and this doesn't work well because your data don't allow you to calculate it to really have this the number of almost susceptibles you don't know. Okay, yeah, you know the number of new infections only, and then with COVID, there are lots of asymptomatic cases and so on, so on. So you cannot really do this. So that's why I'm saying that these models are models that gives you a general view of how epidemics dynamics should be. But if you want really now fitting models and making predictions, that's another story. Maybe we can discuss this later on Friday, how it is about predictions and so on. Okay? Usually with COVID, it has really been very, very clear that it's very difficult to make predictions. Yeah. So that we have this, and this is the characterization of the peak. But then we can also say, for instance, that if n is equal to S plus R plus I, then I can just write S over N equal to 1 minus R plus I over N, and I will call this some G, 1 minus G over N. And this is what? It's the number of people recovered plus the number of people infectious at that moment. Okay, that's the total number of infections that have already happened in the population. Okay, you agree? R plus I is the people that are infected now, plus the people that have recovered. If they have recovered, they have been infectious at a certain point. So this is the total number of infections that has happened at that point. Okay? So this is a little bit better to estimate than S. Okay. Obviously, if you can estimate, then you can estimate S. But from usually the number of people recovered, depending on the if it's a disease that is easy to notify cases, because all cases are symptomatic, then you can know the number of people that have recovered. It's just the integral of the number of, I mean, it's just summing up all the people that have had the disease, plus, well, the I you don't know. But usually the proportion, you can have situations where the proportion of people that are infectious, okay, is maybe small compared to R. Okay, that depends a little bit. Okay, because R is the integral of I, so you have to take an integral plus the value of the variable I at that point. So usually this here, as the positive thing, it's bigger than I. And if enough time you have it enough time, then this can be approximated by R, and R neglect I. So R over N, and maybe this is easier to calculate. Okay, so then obviously I can get here the S star over N equal to 1 over R will mean 1 minus G star over N equal to 1 over R0, which implies that the total number of people that have had the infection at the peak is 1 minus 1 over R0. Yeah. Okay. It is not difficult, but it's a little bit lengthy to show that this is the peak of the number of infected people. This is not the peak of the curve of new infection per day. Okay? New infections per day, okay, will have also the same shape, more or less. Okay? But this peak here is not this peak here. Okay? The number of new infections per day is this kind. Okay? S times I times N. Okay? So you do the calculation. Okay? You have to in order to find the peak, you have to derive this again by t. So you take the time derivative of this, and then you substitute the equations, and then you can do a calculation, which I won't now because it's a little bit lengthy. And then you can show that this peak is always earlier here than here. So when you have an epidemic curve of number of new cases per day, and you see that a peak, it's not the time where you have the peak of the number of infected people. Yeah. And then it is also, maybe we can do this calculation tomorrow. This value here, you remember the vaccination threshold we discussed yesterday. Okay? So if you have a totally susceptible population, and you want to know the fraction of people that you have to vaccinate, then you will get it. The fraction has to be 1 minus 1 over R0, remember from yesterday. Okay, so this would be the herd immunity threshold. Okay, I'm not showing here because I'm not doing vaccination, but this would be the herd immunity threshold. And then you have this typical discussion we had with COVID. It's when you get to the peak, we are at herd immunity. Okay, and then there comes the conclusion, wrong conclusion, that the epidemic is over. It's not over. Okay, you still have here, for instance, have new even if you got through the peak, you still have new infections. It's just they are slowing down. So one thing that is interesting to calculate here is, can we calculate the R at infinity, which is called the final size of the epidemic? Because at the end of the epidemic, when I goes to 0, when I goes to 0, and then you will have some R infinity, okay? And R infinity, so you have N is equal to S plus, at infinity you have this, at infinite time. Okay? When I is 0, okay, got to 0, or it's negligible, then you have this, and you see, in principle, if you can find R infinity, okay, and this is not equal to N, then there is a fraction of people that remain susceptible. Okay? So not all the population will get infected. There's a fraction of the population that will not be infected. Okay? So let me show you how to calculate R infinity with a little bit of manipulations, equations, and so on. Remember you had this. And remember the equation for R. Okay? Plus. Sorry. Okay? So I will divide one equation by the other. So I've done this before. Okay? So this implies ds dr is equal to minus beta s over n divided by mu, which happens to be r minus r0 s over n. It's a linear equation for s in terms of r. Yeah? Solvable. Easy. S of t is s at time 0, exponential of this thing, which is minus r0 times r of t divided by n. Right? So as an equation for s in terms of r, right, this is just the solution, r0 and r of t. Sometimes you get confused, but r with r0 here is not related to the r, so this guy, okay? It's just a notation here, okay? So at the end, I is 0. Yes? Therefore, n is equal to s infinity plus r infinity, which allows us to calculate s at infinity divided by n is equal to 1 minus r at infinity divided by n. And now I can substitute this. Here, I put this at infinity. You have s of infinity, right, equal to s0 e to minus r0 r infinity over n, which implies that 1 minus r infinity over n, which is the s at infinity, is equal to s0 okay, divided by n here. Okay. S0 over n will be this, e to minus r index 0 r infinity. This is an equation only for r0. Everything else disappeared, so I can write this like 1 minus r infinity over n minus s, and here e to minus r0 r infinity equal to 0. Okay? What is this? This is a transcendental equation. Right? You need this thing equal to this thing. So it can only be done numerically. Okay? But I can show that it has a solution. A way of showing the solution is saying, okay, let R infinity, I lost an n here, yeah, I lost an n. Okay. R will be between 0 and 1, okay? R at infinity, okay? R cannot be larger than the total population, but at the beginning it can be 0. So it's between 0 and 1. And if I take this to be R at infinity at 0, then this gives you here 0, 1 minus S at time 0 divided by n, which is always smaller than 1, so this is positive. And at R equal to 0, infinity to 0, then this is at R equal to 1, this here cancels with this one, and then this term here is always negative. So you have no, I made a mistake. Okay. So at R infinity equal to 0, this term is positive, and R equal to 0, this term, R equal to 1, this term is negative, therefore it has to cross the 0, therefore there is a solution for this. Okay. Now, that's a transcendental equation, and what you can do, it's solved on a computer, okay, or by hand. By hand, I mean doing numerically by hand. Nobody does it anymore, but anyway. So this looks like this. If I put R0 here and R infinity here at 1, so this here will have something like this. This is 0, and it grows like this. And this is growing quickly. So if you are at R0 equal to 2, for instance, you will get something which is usually like this. And if you put it at 4, you will have something which is close to 0.95. Okay? So this is nice because this gives you the final size of the epidemic in terms of R0, which can be calculated at the beginning of the epidemic. That's the magic for this. And you see the final size of the epidemic depends only on R0. And this will be true for almost any model. You can do the same calculation. Okay? It's a little bit more difficult, but more compartments and so on, but at the end this is always the case. So R0 determines the final size of the epidemic, and therefore knowing the size of R0 at the beginning can give you some idea about the number of people that can go through infections. Okay? So again, this is a theoretical result, because if you now want to apply this to a real population, you better make sure that the SIR model is actually the best model. And obviously, then in the real world there are many complications. But this still gives you a kind of order of magnitude, right? What can happen. So let's think about COVID. So at the very beginning we had some R0, okay? And difficult to estimate due to asymptomatic cases. Okay, so and not notified. Therefore, you have to somehow say yeah, what's the proportion of notified and not, okay? Because at the very beginning, you have a curve of I, okay? Of I, new cases, new cases, okay? So, but this here might not be the real thing. Maybe there's a proportion of the real thing. What proportion? If they are not notified, you don't know. So maybe then you need field studies to know where you can go and test all the population, for instance, in a small city, and see the proportion between asymptomatic and symptomatic. Okay, so you need studies in the field, right? Then in order to get this here. Okay? So okay, and in the real world also, well, what happens is with COVID, what happens clearly, it can also happen with other diseases, is that people change behavior due to the existence of infection. Okay, so maybe the parameters are the fact that you have an epidemic will change the parameters of the epidemic. So you have feedback. Okay, so that is what we saw with COVID. I mean, they have an infection that is very easy to transmit. R0 was like 2.5, 3, and which would imply over 90% of people getting infected. And at the first moment, what we saw was the original strain that appeared from China and so on, had a considerable proportion of people that died, or the people that got severely sick, had to go to hospital, had also other consequences. So so therefore people changed through the governments or whatever, or people just being afraid, they change the behavior, which changes the parameters of the equations. Okay, so there's a feedback, and this is usually difficult to evaluate for this. Okay, so and this feedback will modify where the R infinity goes, where the peak is, and so on. Everything gets modified. Yeah. So yeah, and then that's the main thing. People change behavior. And then there are other things in the real epidemics that also that can spoil this. One is, as I told you yesterday, when you talk about sexually transmitted diseases, then the network of contacts is very heterogeneous, and this will not apply. And but you can have an SIR thing if you think of a model which is based on individuals. And it's a network of individuals. Every individual can have a state S, I, or R. So you can have an SIR dynamic on the model, but it's not the same as this thing. Okay, it's not the usual compartmental model. You have to do this with stochastic dynamics for the case of networks. Okay? So, but then there are other heterogeneities, like the heterogeneity of people. Well, age is a problem, is a thing, but age is easy. Age is easy. You subdivide S, I, and R into classes that will generate a lot of equations, but it's conceptually okay. As it's more difficult is that actually the probability of contact between one individual that is infected with one individual or susceptible, that this generates a new infected, is not really a constant. Can depend on the people. Therefore, this probability should be a distribution, not a fixed value. Okay? And then it depends on how this distribution is. It could be, if the variance is not very, very large, then usually just the mean will be okay, but could be that it's not okay. And therefore, this would give you, and at the level of the equations, this guy here could be should be drawn from a probability distribution, and then you should take this as a stochastic differential equation. S and R are stochastic, and then you do the simulation and so on. Okay? This is it could be important, and at least in principle. Okay, in principle, part. So, very good. I think that's all. Unless you have more questions about SIR or SIS or I don't know. Yeah, the mic.
So for analyzing adding all of these compartments, just I guess for understanding the effect of adding more and more compartments and subdividing things, couldn't you consider like a continuum limit of this model in the number of compartments, so that there is like a continuum between being susceptible and recovered, and then maybe another continuum in age, and then you can do kind of a field theory of this.
What is done usually is continuum in age, not in. Therefore, if you think that every age class is a compartment, instead of this, you can have that the age, that S, I, and R depend on age. Say A is the age, okay? Then S will be some function of T and I, and the other also. Then you will get ds dt plus dsTi equal to something.
Yeah.
That you can do usually. It has been done from the very principles of epidemiology. And yes, and well, continuum of other things, it's not practical, because this is from the point of view of what people at the public health sector will observe if the person is infectious or not. So you could think about instead of infection, say viral load. Okay, that's a continuum variable. You could do this, and this can be important, for instance, in HIV. Right? In HIV, this can be important because there's a viral. The HIV, you have to do models on HIV. Usually you have to model the pathogen host dynamics in host. Right? And yeah, then it could be viral load. But the point is, okay, HIV is very particular because people get HIV has been a story about if a person knows a person is infected, then there had been a lot of screening, and so you had a lot of people that you knew that had HIV before the symptoms, and then you could follow the viral curve. But this is not the case usually in other diseases. Okay, sure that, for instance, even for COVID, the viral load is important. Okay, but and you have even some idea of individually how the viral load goes and so on, but yeah, you don't get much of this because it's very short disease. I mean, it's 7 days. Okay, so the thing doesn't get very. You don't get anything about trying to the viral load of COVID or diseases like that, but maybe for HIV. More questions? Okay, so see you tomorrow, people. Thank you.